Alright, hey everybody, and in this video we are going to talk about cancer growth, and we are going to focus on the cancer cells. And as cancer cells divide more and more, they can create tumors, which are made up of cancer cells and blood vessels and just empty space, but primarily they are made up of cancer cells, and this can cause serious health issues, including death. And so the typical or the average cancer cell is roughly 20 microns in diameter. And 1 micron is 10 to the negative 6 meters. So the average cancer cell is 2 times 10 to the negative 5th meters. And this is very, very small, but not as small as you might think. In fact, it is roughly the size or the width of a single human hair. And so this is actually larger than a blood cell, a red blood cell. It is larger than spider web silk thread. It's larger than bacteria, and it's much larger than a single virus. And so we can use this diameter of a cancer cell, and we can calculate its volume, and we can use the formula that mathematicians derived a long time ago for the volume of a sphere. And maybe you have it memorized, I do not, or maybe you're able to derive it from the formula we have for a circle, and then we can continue to work our way to the spherical formula. But the formula is volume equals 4/3 times pi times the radius cubed. And this is our volume of a single cancer cell. And of course, not every cancer cell is exactly spherical. We are making an approximation there. Some cells can be quite irregular, but for our purposes, we are going to assume that they are approximately spherical, and so we can apply this formula in addition to everything else. And so now that we have the formula, we can plug in our R and determine the volume. We can determine volume V1. And so let's give ourselves a ton of space. So volume V1 is equal to 4/3 times pi times 2 times 10 to the negative 5th times half, because our radius is going to be half our diameter, and this is our diameter, and this is our diameter. So this equals, I will pause and I will calculate it for you because I haven't calculated it. This is going to be 4/3 pi, and half of this expression is 1 times 10 to the negative 5th. And then we are going to cube this, right? We're going to cube this. And that gives us 4, this is equal to roughly 4.19 times 10 to the negative 15 power. So the 4.19 is 4/3 times pi, and this cubed is 10 to the negative 15th. And so, and this is all meters cubed, right? Because we cubed, yeah, this is meters, and so we're cubing it. And so there we go. This is going to be the volume of an individual cancer cell, the typical cancer cell. And so we can use this to calculate, to find a formula for the rate at which a cancer cell will divide, and that will be useful for calculating the size of a tumor. And so first we have to make an assumption. So that assumption one will be that the cancer cell divides / doubles once every day. And again, every cancer is different. Each cancer cell could divide more than once a day, less than once a day. It really all depends. But on average, we could say that a cancer cell, again, depending on the type of cancer, will double once every day. And so we can derive a formula for calculating this right here using the volume. So we are going to find a formula to calculate the volume cancer cells over T days. And so that formula, we can take our V1, because that's the volume of a single cancer cell, and we can just multiply that by 2, right? Because it's just doubling, doubles, we said. And so, and it's over T days, so we can raise this to the T power, because 1 day would just be times 2. If it was 2 days, it would double twice, so this would be 4. If it was 3 days, it would double 3 times, and that would be 8. So we would multiply it by 8 cells. So that makes sense, I think. So this is the formula to find the volume of all cancer cells over T days. And now we can extend this even further. Now we care, what we care about from a medical perspective is the tumor. Because depending on the size of a tumor or where that tumor is located, it can cause seriously debilitating issues for a patient. And so, we gotta make another assumption about the tumor. Assumption number 2. The tumor is made, let's use a better word. The tumor consists of, let's say, 75% cancer cells, and the remainder is blood vessels and empty space. Blood vessels and empty space. And so we want to find how long it takes for the tumor to reach 1 centimeter in diameter. And 1 centimeter, we could say, is 10 to the negative 2 meters. And so we could write the volume, And so if the tumor reaches 1, we want to find how long it takes. How long it takes for the tumor to reach 1 centimeter in diameter. And 1 centimeter in diameter is in volume. If we assume again that the tumor would be spherical, that is not always the case. In fact, tumors can be quite irregular. But for our case, we will make that assumption. And so we get a 4/3 times pi times 10 to the negative 2 cubed, which is equal to 4.19 times 10 to the negative 6 equals our volume 2. And so we want to we want to know how long it will take for the tumor to reach this. And so to do this, we just plug in our formula. So we want to set V1 times 2t. I want to set that equal to V2. And so I will write it all out for us. So bear with me, I might just skip ahead to it. And so we can begin to solve for our t. Solve for our t. And so to do that, we can divide both sides by V1. Divide by V1. And we get 2t is equal to V2 over V1. And then we can use our logarithmic properties to solve for t. And so we can push that t to the side and get t times the natural log of 2. And that is equal to the natural log of V2 over V1. And then we can divide by natural log of 2. Divide both sides by the natural log of 2 to isolate the t, which is what we want. We want to know the amount of time it takes for the volume of cancer cells to reach a tumor size of a diameter of 1 centimeter. And so we just need to solve. T is equal to natural log of V2 over V1 over the natural log of 2. And so we plug in our amounts and we get, whoops, this looks kind of funny. And so we get natural log of V2, which is 4.19 times 10 to the negative 6. And we divide that by V1, which is 4.1 times 10 to the negative 15. And then we divide all of this by the natural log of 2. And this equals, let me look it up and I'll skip ahead to you. I'll calculate it in a calculator. Okay, and so we get, according to Wolfram Alpha, we get 4.19. All of this calculated, we get to 29.89, so roughly 30 days. Equal roughly 30 days. And that is our answer. So after roughly 30 days, according to this model, according to the volume of the cancer cells, we'll reach a diameter in the tumor of about 1 centimeter. And this could have various different implications depending on the type of cancer, where it's located, how the doctor or physician will attempt to treat it, if surgery is an option, whatever their approach is or strategy. This could be valuable information to know how fast the cancer is spreading. And it depends on the type of cancer, and we made a lot of assumptions. So this is approximately 30 days. It could be 25 days. It could be 35 days. But I think this is a good indicator of what a patient can expect from whatever cancer they have if we knew this information. And so with that, we'll see you in the next video.